Stewart. I'm here to give you some lectures on superconductivity at Professor Antonio Castroneto's request. Superconductivity is an old field, started in 1911, as we'll see. And during my career, I have been told at least 3 times, superconductivity is dead. There's nothing more interesting to find. So the first time this happened was about 1973. And so, we kept doing our work. I was a graduate student. And then John Cavallo discovered niobium-3 germanium, A15 structure, around 23 Kelvin TC, which in those days was high TC. I know these days it's low TC, but it was high TC. So then there was some excitement, and superconductivity wasn't dead for a while. And then things went on, and around, 1979, Frank Steglich published superconductivity and cerium-copper-2 silicon-2, a heavy fermion system, which shouldn't superconduct, it should have been magnetic. And so superconductivity got another boost. So 1974 got a boost, 1979 got a boost, and around, 84, 85 people started saying superconductivity is dead. Well, no it wasn't, because Ben Nordström Mueller published high TC superconductivity in 86. So lately, my head spins keeping up with all the new excitement in superconductivity. So I think if you are at all interested in learning about superconductivity, it's too much. It's not that it's going to die, it's so alive you have to beat it down with a stick. So some of the things that we won't talk about is in this short series of 8 lectures, we're going to talk about monolayer superconductivity. There's currently an 8-degree superconductor, which when it's put on strontium titanate goes up to around 100 Kelvin in its transition temperature. So we'll get to that. But nowhere on here does it talk about superconductivity under pressure. So for instance, Shimizu and Osaka and Arametz, and I forget where he's at, he's based in Europe, have discovered hydrogen sulfide superconduction at 200 Kelvin. So the goal has been room temperature superconductivity, and somewhere in Antarctica there is a room that's 200 Kelvin in temperature, so they finally achieved it. Unfortunately, you need 200 gigapascals, which when I talked to my high pressure friend down the hall, James Hamlin, you do it in diamond cells, and if you go that high, you can guarantee that you broke them. So you get to do one experiment up to 200 GPa, and then the diamond cell, which is around $1,500, $2,000, breaks, and then you start over. So the game of finding new high-pressure superconductors is very strong and very energetic, but there's only a few people that do it, and so we're not going to talk about that, but it does exist out there. So we're going to start with the slow approach to make sure you're all on the same page of understanding superconductivity in a very basic fashion. And so in the attempt to put a lot into 8 lectures, I'm telling you all about superconductivity in an hour? Really? So it's a very dense lecture. There's a lot of, every slide has 10 slides behind it that I'm not showing you. I've gotten it down to 46 slides, which is too many, but that's what we're doing. So feel free to ask questions. Somewhere this lecture will get posted on the web and you can go read what we didn't get to, I guess. Okay, so just to start off with the definition, and people argue about this all the time, but if you're using electron-phonon coupling as predicted by Bardeen, Cooper, and Schrieffer in 1957, Nobel Prize 1972, then I am at least going to call that kind of superconductivity conventional. And if it's not electron-phonon coupled, as described by Bardeen, Cooper, and Schrieffer, then I'm going to call it unconventional. And of course, unconventional superconductivity is the big future of superconductivity, because if you're ever going to get to high temperature, you're going to need unconventional pairing mechanisms. But there are people like Warren Pickett in California who think you can get there with electron-phonon coupling. So he says that hydrogen sulfide is electron-phonon coupled. He says 200 Kelvin comes from conventional pairing mechanism. So there's still arguments about all of this. So I'm not the world's expert, although I have an opinion, so decide for yourselves. This is where the discovery was, and for you students, why is it that Kamerlingh Onnes discovered superconductivity first? He was the first one that had a machine that would let him go there. So all of the millions of dollars that all the universities in Singapore spend for high-powered, forefront, technologically advanced machines, they're useful. So Kamerlingh Onnes managed to liquefy helium, and the amount fit in a cubic centimeter. I mean, we're not talking 100 liters rolled in a dewar to your door when you need it. We're talking, you know, days of work for a cubic centimeter. And so what he did was he said to a grad student, that's what grad students are for, go measure the resistance of a bunch of things. And so the grad student, being a good grad student, went and measured the resistance of a bunch of things. I don't want you to think that they picked mercury on purpose. Who would pick mercury? I mean, right? So the grad student came, I'm sure, to Professor Dr. Onnes and said, boss, resistivity goes to 0. He says, your lead fell off, check it again. And so, if you go look at the data, that's what the data look like. Something around the boiling point of helium. And this is in Leiden, so this is sea level, so that's, you know, helium is liquid up about here, so they did not have to pump to get to here, too much. So the resistance goes to 0, and it's some very small number. And there have been people who spent years trapping currents in superconducting rings, and there's no resistance, so the current is still there a couple years later. So it really is truly 0 resistance, at least in the type 1 simple superconductors like lead. In 1933, a graduate student named Oxenfeld discovered something that we'll talk about, that the magnetic field is 0 inside of a superconductor, and this has thermodynamic implications. It's not just a physical fact that goes into the calculations of the thermodynamic quantities. And so this is Oxenfeld's discovery, and it's always called the Meissner effect after the professor. So I will be one of the few people that talk about the Meissner-Oxenfeld effect. Everyone else will say Meissner. Who cares about the grad student, right? Right. Next lecture, when we talk about applications, we'll talk about the Josephson effect. What was the academic degree of Brian Josephson when he made his discovery? He was a grad student. And there is this fun story that I got from an eyewitness, Walt Harrison, that Brian Josephson was presenting his theory on the blackboard at some small conference, and Professor Dr. John Bardeen got up afterwards and said, that's all very interesting, but it's wrong. Goes up and writes some equations. Theorists do this very well. And Brian listened through, and thank you very much for your comments, Professor Bardeen, and here's why you're wrong. So, anyway, Brian Josephson was a grad student. And we need to be very careful about this statement. Most theorists go around reading this sentence and saying it's true. It's mostly experimentally not true, and I will tell you about that. And in 1957, these guys, which I talked about, figured out a theoretical explanation of what had been known for 46 years. And this is Bardeen's second Nobel Prize. 16 years earlier, he got a part of the Nobel Prize for helping invent the transistor at Bell Labs. Can anyone tell me someone else, there are 3 more, who got 2 Nobel Prizes? Marie Curie, physics and chemistry. Pauling, yeah, it's true. Physics and Nobel Peace Prize, which of course, since Obama got it, we're not sure. And one more, Some guy that did protein tracking, I forget his name, he was a biophysicist, chemist, got into chemistry, got 2 prizes. So there's actually 4 people. And now, exciting in superconductivity is this, and you say, well, gosh, here we are in 2018, that's 32 years later, there's a whole lot more people working on superconductivity than there were in the old days. Do we have a theory to explain it? If you talk to individual theorists, they'll say, sure, my theory explains it perfectly. However, if you go to the theorist down the hall, you say, well, what about so-and-so's claim that his theory explains it perfectly? Oh, that's all hogwash. My theory explains it perfectly. So there's still disagreement about the cause, and speaking as an impartial experimentalist observer, I would say they don't know. And it's unconventional for sure. No one thinks it's electron-phonon coupling like BCS theory, and there are actually experimental proofs that it's not conventional. So there's no argument about that. Now here is the Meissner-Ochsenfeld effect. Ta-da. And here's magnetic field, here is temperature, and if you cool in magnetic field, so magnetic field is finite along this D to E line. If you cool through the superconducting transition temperature, which is a function of field, so it's this high at temperature in 0 field, and it's at T equals 0, it has a critical magnetic field of this much. So if you're somewhere in between 0 and the critical field, this is the superconducting transition temperature at that field. If you cool through that, in ideal rare cases, you go from here, so above TC, you have a bunch of field lines penetrating your cylindrical sample. This is so you can get the demagnetization coefficient nicely. And if you go below TC, going along this point, in ideal, perfect, this is what all theorists believe conditions, the flux is expelled. This almost never happens. I had this discussion with a theory colleague in the University of Florida Physics Department who will remain nameless because he thought this was really true. Well, if you read the original Meissner-Ochsenfeld paper, they did 2 elements. They did tin and they did lead. And if you read their data, lead looks like that. Tin has vortex pinning that prevents flux expulsion and looks like this. So this is just some data out of a file that I carry around with me. This is an iron-based superconductor. This is not quite the best stoichiometry for TC, but you know, here's a transition temperature, and if you cool it in 0 field, which would be along this line, right? Then you get down to here, then you turn a small magnetic field on, and you measure the susceptibility, and it looks rather diamagnetic. In other words, a -1/4 pi would be perfect diamagnetism. So on this scale, it might be a little further down here. But anyway, you get what's called shielding, and it looks pretty diamagnetic, it looks pretty superconducting. However, if you cooled in field, which would be the line that was shown to you here, these conditions, if you cool in field, you get this little teeny tiny, I think you can see it, amount of flux expulsion. And that's what the Meissner-Ochsenfeld data for tin show. If you can read German, you can go read it for yourselves. It's not total flux expulsion, only in lead, where there was no flux pinning. And the flux lines in this picture get pinned to impurities, and it's a big study. So it doesn't matter what kind of superconductor, we're going to talk about that now. You can have type 1 superconductors, which if you look at the negative magnetization, remember this is diamagnetic, up to the critical field, a type 1 superconductor expels the flux, perfectly diamagnetic, and at some critical field, all the flux rushes in and it's entirely normal. That's called a type 1 superconductor, and you get flux pinning in both kinds of superconductor. And for those of you who like to study thermodynamics, the condensation condensation energy of a superconductor, the difference between the free energies in the normal and the superconducting state, is the critical field in a type 1 superconductor squared divided by 8 pi. So that's actually a useful piece of information to know if you're worried about energetics. A type 2 superconductor it's perfectly diamagnetic up to some lower critical field, which is known as HC1, which can be quite small. And then flux lines start to penetrate in. Here are some flux lines in the terbium, barium, copper oxide, high TC cuprates, which we'll talk about later. Please notice that this is in no sense an ordered lattice of flux lines. The black spots are flux lines. This is fairly random. We'll come back to that. So anyway, from this point, HC1, up to an upper critical field where the entire sample is threaded by flux lines and it's entirely normal, that's what happens to the superconductivity. Now you get resistivity that's zero by having connected pathways that don't have to go through a flux line, and so you can have some amount of diamagnetic susceptibility, as you see, right? It's not perfectly diamagnetic, but you still have some diamagnetic susceptibility. You have rho equals 0, but no problem with zero resistivity, and you have practical a wire for making superconducting magnets. So type 2 superconductors are what are used industrially, and this is a very important distinction. Just to give you some examples of type 2 superconductors and the two critical fields, and I will always reference the critical magnetic field as being at T equals 0. I will always reference this one down here. It doesn't make any sense to reference anywhere along here unless you specify the temperature. So when you see a critical field, it's almost always the low temperature T equals 0 extrapolation. So in niobium, which is one of, I think, approximately 3 type 2 superconducting elements, the lower critical field is this much in units of Tesla, and the upper critical field is not much more. So there's not a big ratio here. If you go to niobium 310, which is the A15 structured superconductor discovered in 1954 by Gregory and co-workers, including my thesis advisor, actually. I have to throw that in as an advertisement. This has a very high upper critical field and is useful in high field magnets, which we'll talk about in lecture 2. Okay? So a picture of flux lines. Here are the critical fields versus temperature for niobium 310. It's obviously a type 2 superconductor because here is or depending on whether you're talking in the superconductor or outside the superconductor, here is HC1, PC1, rather low number. Notice that this is lower than it is in niobium, for example. And here is the upper critical field, 24.5 Tesla. Now, for those of you who had another summer or two, I could lecture you on how to make niobium 310 a little bit better. So there's a guy named Showa in Japan who makes the world's best niobium 310, and he has all these chemistry tricks where he dopes a little bit of this and a little bit of that, and he gets better flux pinning, and gets a little higher critical behavior, a little higher. So when I started giving this talk some years ago, the upper critical field for a commercial magnet that you could buy from Oxford was 21 Tesla. You went to Oxford, you say, here's my $1,000,000 US, none of this Singaporean stuff, here's my $1,000,000 US, please sell me a magnet system that goes to 21 Tesla. And Oxford would say, yes sir, yes sir. And in a year you'd get it, if you were lucky. Sometimes they'd say, we failed, here's your deposit back, because it was very iffy. These days, using superconducting conventional wire, conventional superconducting wire, you can buy one at 23, 23.5. Because old man Showa is over there doping the little cannellum, doing a little stretching, doing a little quenching, doing a few tricks, and he just walks it up. And you say, oh, Professor Stewart, I can be 24.5. Why can't they make that? Well, because when you're that close to the critical upper field, you don't want to make a magnet out of it because there's all those kilojoules of energy in there that come out because there's this huge inductance. So actually the inductance of our 16 Tesla magnet is 17 henries. So there's a whole lot of kilojoules in there. And when it quenches, it's an exciting event. I mean, all the helium comes out, just this big gas front. So you want to stay a little bit away from the theoretical upper. And the other thing is, I might point out, no one runs their superconductor at T equals 0. We haven't quite gotten there yet. Even in the millikelvin laboratory at Gainesville, still 1.9 Kelvin maybe. So again, this is 10 lectures. This is what we talked about for an item 310. It's normal. You cool through this phase transition line. This is second order phase transition. And you get into a vortex lattice. Remember when I showed you for the cuprates, that's not a lattice structure, ordered structure of vortices, that's a glass. But in a type 2 like 91310, they're regularly arrayed, triangular, usually some equal spacing, vortex lattice, and down here, of course, is the Meissner-Oxenfeld effect. So in a high TC cuprate, there's this mean field, upper critical field here. Below that, because of thermal fluctuations, which I'm not a big expert on, but which is very important in the cuprates, it's not a frozen thing, it's a vortex fluid, so the vortices move around. This means that when you put a current through it, there's losses. F equal V cross B. F times distance equal work. There's losses. If the vortices can move in the fluid, you get losses. So this is not where you want to run your high temperature superconducting cuprate magnet, because you'll be pumping energy in for the rest of its life at those fields. So the High Field Magnet Laboratory in Tallahassee put into operation for users, which is very courageous because users are rough on equipment, I believe it's a 33 Tesla high TC cuprate magnet in this calendar year. So it's available for user use. So it is possible to get a high field magnet above 23 and a half that you get from the old high TC A15 structure in algorithm 310, which again we'll talk about in lecture 2. And it's a great challenge. I think the magnet cost $5 or $6 million, and there was no profit motive in that number. Obviously, when Oxford sells you a magnet for $1 million, oh, trust me, it didn't cost $1 million to make. But the Magnet Lab is quoting what it cost the Magnet Lab to make, and it's the $5 or $6 million magnet. And then below that point, because of all the pinning that goes on in the cuprates, it's more or less for sure a vortex glass, not a vortex lattice. Okay? And cuprates are in their nature full of defects because, of course, as we'll learn in some lecture or other, the amount of oxygen that goes in is very critical. That's a humorous play on words. It's very critical to the superconductivity because we're talking about critical temperature, field, current. The composition is very important. Yeah, cuprates have defects. So back when I was a youth, there were some really impressive experiments using Squid Magnetometry, looking at the fluctuations around the superconducting transitions. And according to Professor Antonio, you guys are mostly interested in 2D and 1D, so obviously fluctuations are more interesting in 2 dimensions or 1 dimension. So I thought I'd throw this in here. So above TC, you can have fluctuations that give you an excess conductivity. So resistivity is a little low. Gives you some diamagnetism, which is a lead pipe sense to measure. Gives you an effect in the specific heat, which is my field of expertise. And you can have some tunneling currents. Below TC, you can have these other kinds of fluctuations. And when you get into thin films, you're just into fluctuations. And the nice thing about thin films is you can drive the superconducting critical field way past what it is in the bulk. So you can run thin film superconductors to like 4 times the normal, what you would think of as the upper critical field. So the tape geometry for winding superconducting magnets is a little challenging, but it's heavily used. Okay, so I just thought I'd give you an example. This is totally ahead of time. Lecture 3 is going to talk about the intercalated and layered dichalcogenides. That's a chalcogen sulfur. So if you intercalate this with some evil chemical called pyridine, and I cannot write the chemical formula down for you, you can spread the superconducting layers apart and make it more and more and more and more two-dimensional. And then you can look above TC for the fluctuation diamagnetic susceptibility. And this was in the early 70s. And what they disappointingly found out was it sort of matched the data for a bulk 3D material. And so it turns out, due to weak coupling between the tantalum sulfide superconducting layers, it actually showed 3D fluctuations up to some crossover temperature, but their data wasn't accurate enough to get good data up there. So all they could talk about was 3D fluctuation. So it wasn't terribly exciting. This was still a tour de force. The size of the diamagnetic susceptibility they're talking about here is sort of, depending on how proud you are of your magnetic property measurement machine from quantum design, is sort of doable in a commercial machine using their commercial Squid and their electronics. This was, of course, a homemade surface scanning Squid Magnetometer from Dan Prover, who later went to Yale. So at the time, this was certainly a tour de force to see those small diamagnetic susceptibilities. So another consequence, I'm not going to spend a lot of time in the application talk talking about Maglev, but it's obviously a possible reality. I believe the Japanese have a rather short section of Maglev going on. I think the Chinese are also spending money. It's not really there yet. It's not really practical, but people do it to show how much money they can throw at a project. I mean, wouldn't you really rather take a subway in Singapore that wasn't going to crash because of some technical glitch in the Maglev design? You'd probably just take a normal subway, right? So it's not really meant for passengers, although it's used, I think, between some airport and some city in China. It might be Shanghai, I don't know. Anyway, everyone has a comfort location in their field. This is my comfort location. I have spent a lot of time with simple elements. Bernd Matthias, before he died in '81, whenever he would give a lecture, he would show his periodic table of the elements. Okay? And if you want a quote from a person no longer with us, if you make a metal clean enough and cold enough, it will either be magnetic or superconducting. That's a claim, right? So if I go back to this slide, you'll see that silver is neither in this slide. However, if you want to go to 560 picokelvin, probably not something you're ready to do in your lab here. This is in Olli Lunnasma's group in Finland. You can find out that silver is antiferromagnetic. So Matthias has proven right yet again. We won't spend a lot of time worrying about really, really, really low temperature. I would just say that when you go on the internet, which is the source of all incorrect knowledge, you will find some versions of this table that have gadolinium as being a superconductor. No, it's not. It's antiferromagnetic. I mean, it's really not superconducting. No one says it's superconducting, but this table has this mistake in it. And again, we could spend a long time, although elements are sort of boring, we could spend a long time arguing whether uranium at zero pressure really is a superconductor or not. I think the right answer is probably no. I think you need some internal strain to make it superconduct. This is a rather tricky one. Americium, I was part of that original project at Los Alamos. Americium-243, which has a half-life of 7,000 years, superconducts at around 0.7 Kelvin, and all these other things. So under pressure, obviously, as I talked about on the introductory slide, pressure is the current frontier. Diamond is, if you dope that, I think it's boron. If you dope this, you can make it superconductor. And so for a while, around 2004, that was a big topic, but it died away. So here's the more up-to-date slide for pressure. So this is very hard to read, and I asked the author of the picture to send me a more accurate, high-resolution one, and he managed not to do that. He felt free to ask me something else, but he didn't supply this. But anyway, if you try to read it carefully, you can see that you can raise the TC of vanadium, which at room pressure is sort of like a 4-degree superconductor. If you go up to 1.2 megabar or 120 gigapascals, whatever you're most comfortable with, you can get a TC up around this number. Matthias liked to say, no theorist ever predicted a real superconductor. And just after he died, in 81, Marvin Cohen at Berkeley published the prediction that if you put silicon under pressure, that it would superconduct. And he got it mostly right. At 15 GPa, it superconducts at 8.2 Kelvin. So actually there was, after Matthias died, they used to compete with each other at meetings and claim each other had said something wrong. After Matthias was gone, silicon was experimentally proven to be a superconductor under pressure. Now, of course, it's a cheat. It's no longer the diamond structure. It's another structure. But anyway, some of these numbers are really out there. I mean, the fact that calcium superconducts at 29 Kelvin at 2.15 megabar, I'm not sure we're all caring about that. Back when, in the 70s, I was working with someone who was doing A15s that didn't want to form in that structure except under high pressure. We were happy with a megabar, and we got that from plastic explosives down in one of the canyons. So the fact that someone can DC put on 2 megabar is, that's a lot of work. So this graph shows you that the frontier of where superconductivity might be, a la Matthias, is rather open. And of course, silver is a nice low temperature record. Now here's another graph out of, I think this is Wikipedia, and of course it's all wrong. For instance, technetium, this is not transition temperature, this is an element. Technetium doesn't have anything like these numbers, it's this if it's pure. Niobium does not have this for an upper critical field, it's more like 0.4. And of course they forgot beryllium, which if you cool it off to 26 millikelvin goes superconductor. So that's just an overview of what some of the numbers are. This is an overview of some of the compounds. This is the record, which when you put it under pressure goes up to 150 something, and of course now we have the hydrogen sulfide, otherwise known as stinky gas. And so here's a timeline of superconductivity. Here's Camerlingionis, a grad student back in 1911. Here are Bednorge and Mueller in 86. And of course here's Paul Chu a very short time later. And you might ask, how is it that someone made this leap? Notice how gradual these are. How is it that someone made this leap? Well, everyone has their favorite measurement technique. Paul Chu's favorite measurement technique is give me a superconductor and I will put it under pressure. I don't care which superconductor, I'll put it under pressure. I don't care if it's boring, I'll put it under pressure. Pressure, pressure, pressure. So Paul Chu took this stuff and he put it under pressure. Notice the TC went up 20 Kelvin. Now that's a record. 20 Kelvin for 10 kilobar, that's a lot. Oh, excuse the units. 10 kilobar, wait. That's a gigapascal, right? I don't know, anyway, 10 kilobar. And said, I know, I'll use chemical pressure. This has got lanthanum in it. I'll take an element that's smaller, yttrium. I'll stick it in. Now, Paul Chu had no idea what the structure was. He was just shaking and baking, making ceramic powders. He wasn't really a materials guy. He was a good pressure on things. And he discovered a 92-degree superconductor. And when was it the outside world knew about Paul's discovery? way before. The outside world learned about Paul-Chew's discovery when he asked for magnet time at the old magnet lab at MIT. And he called Jean Morrison, the secretary, and said, or she called him and said, oh, Professor Chew, you're down for looking at critical currents of a new superconductor, name unspecified, people were like that. How much liquid helium do you want us to order for your visit? Answer, none. That's when the world knew. And Jean told us all. It was great. So he just needs nitrogen. I will tell you another Paul-Chew story. This is true. I've heard it from both the former editor of Physical Review Letters and from Paul himself. When he submitted the letter to PhysRev Letters, it obviously is going to go to referee. And we all, of course, swear that when we get an article to review that no, we would not run into our lab and start working on it. Unless, of course, you worked at Bell Labs and were sharp. So anyway, he sent it in for refereeing, and instead of yttrium, he said he'd used ytterbium, YB instead of Y. This is a true story. Okay? So 2 weeks later, after it was reviewed and accepted and it was ready to go to press, Paul called Jean Wells, the editor at PRL, and said, oh, Jean, I'm so sorry. I have a new secretary, and she doesn't quite know the periodic table yet. She did a typo. It's not ytterbium, it's yttrium. And of course, Jean Wells was very angry because he knew what Paul had done. Didn't trust PhysRev Letters to keep a secret. Said, okay, we'll change it. And it got published. Coincidentally, rumor has it that Bell Labs had been working vigorously on trying to make ytterbium barium copper oxide during those 2 weeks. Without success. And the cherry on the story, on the pie of the story is, if you do it right, ytterbium works too. So they weren't only thieves, they were incompetent thieves. But that's okay. And these days, if you're going to submit the greatest discovery since sliced bread, you might want to change the elements around a little bit and then right at the very end correct it. So the latest set of high TC, quote unquote, materials were discovered in Hosono's group in Japan. He actually published this one in '06. And if anyone had been awake, they would have said, oh, look, an iron-containing superconductor. Oh, look, phosphorus. I know, I'll look at my periodic table and I'll substitute arsenic. It wasn't a terribly hard concept, but since it was only 6 Kelvin, no one did it. And Hosono just kept working along steadily, slowly, and 2 years later, published 26 Kelvin for this material. Okay, so notice there's no difference. It's just lanthanum, oxygen, iron. Well, okay, there's a little fluorine in here. Phosphorus, arsenic. But anyway, this was not a great mental leap. And then it took off. The Chinese were the ones that are going to beat us all to the finish line in their research because they have such large groups and such large amounts of money. Within 6 months, we're up here. And there were a bunch of competing compositions, not just the strontium. And then slowly things moved up, and this is under dispute. I am informed by a theory colleague that I shouldn't say that this is a known fact. Only one group has gotten to 106, I think. Other groups are talking about 60 and 70 Kelvin. But it is without doubt that if you take this 8-degree superconductor, which would be down here somewhere, and make a monolayer, not a bilayer, a monolayer on strontium titanate, and on a few other dielectric substrates, it doesn't just have to be strontium titanate. You get around 70 to 100 Kelvin. And here's hydrogen sulfide. I thought it was higher, but okay, they say it's only 1.55 megapascal, and it's slightly above 200. And this has been confirmed. This is an agreed upon number. Okay, this is still being argued about. This is an agreed upon number. So not only is superconductivity not dead, it's cooking along rather rapidly. So who knows where this next goes? I mean, if it's anything, and this is pure fun, if it's anything like Bednorz and Mueller's discovery, or if it's anything like Hosono's discovery, this will rise quickly. At a talk 2 years ago, I asked Shimizu, what other materials are you looking at? And he was quite willing to tell me the ones that didn't work. But the ones that they're still working on. And James Hamlin down the hallway has got material for me. Everyone's off in their corner, hiding their compound from phys rev letter, and trying to do things. We're looking at other light atom compounds. There's a hint there. We're looking at other light atom compounds, and we're not doing hydrogen because, trust me, Shimizu and Arametz have buried it. If there's a hydride that exists, they've looked at it. So it's a very competitive field. Since I presume there are a lot of theorists in the audience, I briefly make a foray into theory. So we're going to have a complex order parameter, psi. The absolute magnitude of psi squared is going to be proportional to the density of the electrons, which makes it useful. And in simple Ginzburg-Landau theory, put together these terms. You minimize the free energy with respect to fluctuations, and you get this. And moving right along, here's a few caveats. Minimize the free energy with respect to the electron density, get this. So this turns out to be an important ratio of parameters. And of course, if I showed you that important ratio of parameters without telling you where it came from, you'd want to know where it came from. But when you introduce the magnetic field, it looks like that. But anyway, here we go. If you take the ratio from that original Ginzburg-Landau equation, where alpha is the coefficient of the psi squared term, and beta is the coefficient of the psi of the fourth term, if you take the ratio this way, this is condensation energy, and if you take this ratio, it involves 1 over the mean free path. Wait. Penetration depth, thank you. Who said that? Someone knew that. Okay, good. Keep me honest. I'm trying to talk fast. It's hard. Okay. Yes, that is the penetration depth, which we'll talk about a little bit more in just a minute. So here's the coherence length. Here we go. Here's the coherence length, again involving the Ginzburg-Landau parameter and the penetration depth, which actually came before from the London theory. And let me just talk about what these actually mean physically. The coherence length, if you have a superconducting electron pair, and they have some pairing interaction, let's not argue about what the pairing interaction is, but you want to know how far apart the electrons in the superconducting pair are coherent with each other in some quantum mechanical state. It's this number, which can be rather large in terms of lattice spacing. And if you want to know when you put a magnetic field on a superconductor and the superconductor expels it, all right, it's not a discontinuity at the surface. There's some penetration of the field. There's some surface currents that are doing the shielding, and that penetration depth can be thousands of angstroms, and it's like this. So making a thin film, you can make a thin film less than the penetration depth and run your critical behavior upwards. The ratio between the penetration depth and the coherence length is called kappa, and I know this is a lot to remember, but if it's a type 1 superconductor, you have a smaller kappa, so you have a larger coherence length with respect to your penetration depth. And if it's a type 2 superconductor, which is talking about the energetics of letting the flux lines penetrate and lowering the energy while keeping part of the sample superconducting, and you have this, well then you have a penetration depth that's larger than the coherence length. So all of the elements are type 1 except those 3. And we talked about, we actually talked about technetium, which is a non-naturally occurring element that comes out of nuclear reactors, Technetium 99, at least when I worked at Los Alamos. Al Georgi got that from Oak Ridge and vanadium. And we talked about how the ratio between Hc2 and Hc1 for niobium wasn't all that large. It was maybe a factor of 2. And of course, for some of the A15s, it's huge numbers. So let's talk about the BCS mechanism. These are a bunch of cartoons that are more or less mostly incorrect, but they'll give you a flavor for the theory, okay? So, if we pair the electrons, we make them into bosons. They're no longer fermions. They can occupy the same energy state. We get Bose-Einstein condensation of Cooper pairs. Now remember, Bardeen, Cooper, Schrieffer. This is Leon Cooper, who was at Brown University. Bardeen was a professor at the University of Illinois, and Schrieffer was. Yes, and Schrieffer, goes the story, and I heard this from Schrieffer in some lecture, was getting tired of working on this, not going anywhere, subject of superconductivity, and went to Bardeen and said, couldn't I work on ferroelectrics? They're much more interesting. Remember, this was in the middle 50s, which when ferroelectrics were hot. And Bardeen said, Bob, wait a little bit, give it 6 months. So there you go. When your thesis advisor tells you, wait a little bit, give it 6 months, just say, oh, please, please. So there's a lot of quantum mechanics mixed in here in the superconductivity, which I really will not have time to touch on. But the neat thing that Cooper showed was if there's a slight amount of attraction between the electrons, it's enough to condense into a superconducting ground state. It doesn't matter how small the attractive interaction was, if it's finite, you get condensation. And this is where my upcoming cartoon is going to look wrong, but anyway, if you pair the electrons, they have equal and opposite momenta in K-space. I'm talking real space, I'm talking K-space, and they have the opposite spin, so they're a spin 0 boson. And the size of this pair, as we discussed, is something like the coherence limit. So here we have an electron moving through space in K-space, and we have some virtual phonon being exchanged between them. We have a net effective interaction, and the point about this interaction is it's a retarded interaction in time. And so this cartoon is not terribly correct, but it will hypnotize you into thinking it's useful. One electron goes through and distorts the lattice. Another electron goes through and sees the influence of the electron that already left the area and took its giant 1 eV Coulomb repulsion with it. Because remember, the attractive interaction between these paired electrons is the order of milli-electron volts. So if the Coulomb repulsion from the first electron is still around, you're not going to get a net attractive interaction. Now, one interesting thing, when Steglich came up with this heavy fermion superconductivity in 1979, the reason people didn't believe it, Matthias amongst them, Matthias didn't believe it, I think, until his death, was because you saw how one electron distorted the lattice and got out of the way, and the other electron came through and saw an attractive interaction effective to the first electron by the distorted lattice, right? A heavy fermion is heavy, and the electron moves through the lattice very slowly. And so the electron in a heavy fermion system hasn't moved out of the way before the next electron could come by. And so the idea was the attractive interaction there could not be BCS, and in Matthias's mind that ended the discussion, so therefore it couldn't be. Now, of course, if you have an unconventional pairing mechanism like exchange of spin fluctuations, it's a whole other question. Okay? So this cartoon at least serves to describe to you why heavy fermions in 1979 were unusual. So under the BCS, and everybody that's here that's a student should memorize this. according to the BCS theory, the transition temperature should be inversely proportional to the square root of the mass. And a lot of this early work was done at Bell, and Bell had money. So when Bell said, hello, supervisor, I need to buy a bunch of enriched isotopes so I can do measurements of superconductivity and write a nice paper, the supervisor said, oh, sure, fine. Oh, sure, fine. And so if you look at the early experiments, I mean, they have all these isotopes. I mean, they're like 7 or 8 or 9 mercury isotopes, various enrichments, but they have beautiful data, beautiful. And they get a pretty accurate agreement with BCS theory, okay? Around 1 over square root of mass, pretty accurate, okay? And then, of course, the fly in the ointment came down. My thesis advisor was at Bell, down the hall, and started doing this sort of thing on ruthenium. Well, if you look at the TCs of ruthenium versus the isotope mass, it doesn't look like that at all. And so my thesis advisor goes to the story, was hopping up and down saying, oh, look, something that kind of makes BCS. And then another office down the hall, Phil Anderson, I think, had this theory that described it still within BCS theory. And so my thesis advisor goes to the story, was all deflated. Oh, darn. You know, for 2 weeks he thought he was famous, right? He contradicted BCS and he had the data to prove it. Oh well. So a lot of things don't follow this but still have electron-photon coupling. It turns out in the high TC cuprates, the one that Bednorz and Mueller discovered, the lanthanum, they doped it with barium, it's now strontium is used, lanthanum, strontium, barium, copper, so 2 lanthanums, 1 copper, 4 oxygens, dope a little bit of the lanthanum, we'll talk about that, with strontium and barium, and you get superconductivity. It turns out that has an isotope effect. If it has an isotope effect, there's electron-photon coupling. If it doesn't have an isotope effect, remember it could be ruthenium, right? It still could be BCS. So isotope effect, yes, it's conventional. Isotope effect, no, you're not sure. You gotta be a little careful. But just walk down the hall to Phil Anderson and ask him, if you can find Phil down the hall. So, high TC, the final frontier, layered structures, lots of 2-dimensionality. You guys want to hear about restricted dimension superconductivity. This is a good start. Here are the actors. The interesting thing about this was Alex Mueller had a theory for why he should go be looking in a nook or cranny for superconductivity where BCS said not to go. BCS said high electronic density states at the Fermi energy, TC, high TC. So he was looking at things that didn't have a high electronic density states, and he had a theory to describe it. His theory was wrong, but he looked in the right place to find something. So don't let the theorists bully you. They could give you insight as to what you should be looking for. And after you have data, they can give you insight to make it fancy for the referee of nature. But theory isn't everything, as Matthias would be fond of telling you. So the interesting thing was they were working in an uninvestigated corner of materials physics that they had no competition. There was no one, they didn't hear the thundering elephant feet behind them trying to catch up like Shimizu and Aramatz are both busy looking at each other, which hydride compound have you looked at lately? There was no one competing with them. So what Mueller did was he measured the resistivity and it went superconducting. He said, well, that's good, but we need to measure the diamagnetic susceptibility. Meissner-Ochsenfeld, since he's German speaking, Swiss actually, he would know all about Meissner and Ochsenfeld. So we need to measure the susceptibility. So he goes to a supervisor and says, hi, I'm distinguished Professor Carl Alex Mueller. Wouldn't you like to go buy a $300,000 machine for me so I can measure the susceptibility on one sample? And the supervisor said, sure. So the delivery time was about a year. So they did something else, probably worked on this for a year. The machine came, they measured, they published. Trust me, Paul Chu did not sit around for a year waiting for some machine to be delivered. Within 2 weeks of Paul Chu's discovery, 3 other labs in the world had made the same discovery because Paul made the mistake of publishing his pressure data. And everybody knew you should go put in a smaller element for lanthanum and go look for high TC superconductivity. Jack Crow at Temple, a Chinese group in Beijing, and I think the Japanese somewhere. So there was a thundering herd behind Paul Chu's back, but these guys, they had it, it was all theirs. And Mueller sent a preprint to my thesis advisor. He didn't worry about someone competing. He was so out of left field, it was his. And notice how Bardeen, Cooper, and Schriefer, with a correct theory, which was acknowledged to be correct, even when ruthenium was up there for 2 weeks, took 15 years to get the Nobel Prize. These guys took a year. And that's the way it is these days. You know, things are much quicker, much more rapid. Things get recognized more quickly. So yeah, these guys got the Nobel Prize, I think, the very next year after their, yeah, there it is. They published in '86, they got the Nobel Prize in '87. They hardly had time to rent a tuxedo before they had to get on the plane to Stockholm. So here's the crystal structure, which Mueller and Bednorz didn't know about. They were doing shake and bake. They sort of had an idea, but they didn't have it refined like Kava did at Princeton somewhat later. So there are layers of copper surrounded by oxygen. So I know this is a little hard to see, but the copper are the red ones, and they order antiferromagnetically. If you don't dope it, it's an antiferromagnet. They order antiferromagnetically in their plane. There's the moment on the red dot at the middle, which you can barely see. Here's the moments on the red dots down in this layer. And then the oxygens are around the coppers. The interesting thing is, this is d-electron superconductivity. So if you want to know what the pairing mechanism is, you better start thinking about spin fluctuations. And all the theorists are still arguing about what the pairing mechanism is, and there is no accepted answer, but they're all pretty sure that spin fluctuations are probably important, because it is d-electron, as in carries a moment, superconductivity. Probably has something to do with magnetism. So here's a bunch of nomenclature. I talked about YBCO earlier, although I did translate it for you. It's either known as this, which is the correct way to talk about it, or this, which is the shorthand, or just 1, 2, 3. We all call this BISCO. So bismuth, strontium, calcium, copper, oxygen. This is called BISCO. It's very two-dimensional, much more so than this. And this is the discovery compound. Again, people prefer the better quality sample again using strontium versus barium. This is the record holder. We talked about that. That's some early data. Resistivity is linear above here, up to a very high temperature. Here's the picture again. They're antiferromagnetic insulators, so you need to, in a big gap, so you need to dope them with something. Strontium, little hole doping. Here's a phase diagram. So here's hole doping over here. Here's electron doping over here. Here's the superconducting dome. Here's a spin glass, little complication down there. Here's antiferromagnetism. Here's the superconducting dome. Here's a region of coexistence. So people get all excited about coexistent, long-range antiferromagnetism and superconductivity. And here's a region of dispute. I will not enter into this dispute. I have never published a paper in electron-doped 214. Something interesting going on there. So, again, another phase diagram. I'm rushing because we're almost out of time. We talked earlier about how you can have a current circulating in a ring for a long time. You can also track flux. And this is the unit of flux. Oops, sorry. This is the unit of flux. And remember, it's paired electrons, so there's a 2 here. And for people who are bad with units, which includes me, because the school I went to wasn't big on units in their freshman physics book, a Weber per square meter is units of Tesla. So field intensity. Talked about that. The flux in the ring has to adjust itself to the external flux. We'll talk about this next time when we talk about Josephson effect and tunneling. I just just throw this in. So if I take an insulating layer, one is superconducting, one is not, and Giever showed that there was something called Giever tunneling, which is, not much conductance through the barrier, and then you exceeded the gap, and then on the superconductor side, and then you get conductivity that looks like this as a function of voltage. And so sharing the Nobel Prize with Giever was Brian Josephson and Leo Isaki, and these are the three flavors of Josephson effect, or two flavors, and then quantum interference, which is, of course, very important in devices these days, and continue next time.